you have a free TV port, you have a closed loop bandwidth, you have a UAT gain frequency. So when you look at the op-amp, right, you will find that they have a UAT gain frequency. Right? The UAT gain frequency is the op-amp specification. The closed loop gain is also depend on your design. The bandwidth related to the closed loop gain, right, is called closed loop bandwidth. Remember that the design formula, right? 0.35 over bandwidth closed loop. This is the one you need. When you set the closed loop gain, you set the closed loop bandwidth. And closed loop bandwidth is depending on the closed loop gain. So you can see that if you have a closed loop gain in here, you will be closed loop bandwidth. When your gain is a 1, so your closed loop bandwidth is a UAT gain. So the maximum UAT gain bandwidth, right, is a 1. Now the area under this diagram, the area is the same. You look at the area in here, right? The dotted line, right, will be equal to the area in here. And also the area in other, the intercept point between this and this. So you can say a constant area. The area is a constant. In the limit is a 1 times Ft. So op-amp characteristic is a one-pole system. Gain bandwidth product is a constant. Okay, this is an important property you need to know. And we have when you have a VDB point, the gain is a A0. Under high gain, the VDB, right? And also another area depends on your closed loop gain design. So because of this property, right? You can see that the roll-off characteristic for one pole is a minus 20 dB per decade, meaning that the gain will drop 10 times, right? With increasing the frequency by 1 decade. What is my decade? Decade means 10 times. For example, right? This frequency in here is a 100K, right? This frequency is a 1 meg. So from here to here, right? The gain will drop by 1/10, 1 over 10. If you 20 log 1 over 10, it is a minus 20 dB per decade. For example, the gain in here is a 10 times. You have 100K, is a 10 times. So you will drop 20 times. You will drop drop 1 over 10 times, right? At that time, is a 1 meg. So you be very careful about this property, right? Gain bandwidth product is a constant. All the area of the rectangle, right, is an area, the gain bandwidth product is equal, right? Depending on what area you want. So if you want high gain, you have a small bandwidth. You want wide bandwidth, you have a low gain, closed loop gain. So it's a trade-off. You cannot high gain, wide bandwidth, no, because the gain bandwidth product is a constant. If you design 1 meg, you only gain is a 1. If you design 100K, your gain may be 10 times, right? So gain bandwidth product is a constant. Okay, so this is an important property. 1 over 10, the rate of drop by 1 over 10, if you 20 log, 20 log is there's a 20 dB, right? Minus 20 dB per decade. This is a characteristic. Okay, so the closed loop gain, multiplied closed loop bandwidth equal to A log times this is a low frequency VDB gain, right? The area equal to another limit area 1 times Ft. A log open loop gain, ACL closed loop gain, VDB cutoff frequency, Ft is a UAT gain frequency. Okay, because of that, right, you can see that this formula can easily derive. If you look at the closed loop frequency, right, it will be closed loop bandwidth, right, UAT gain bandwidth over closed loop, because 1 dot Ft, right, 1 dot Ft means Ft, right? If you are using the closed loop gain, A0, right, A0 FVDB, divide by ACL, then can find the closed loop. Okay, now A0 will be given if the non-ideal op-amp, right? FVDB also given if you want to find this. So this is a characteristic of non-ideal op-amp. Gain bandwidth product is a constant. You can see that you have another important one is a feedback factor and the causal gain. Now look at example here. Okay, now this is a non-inverting amplifier. So the non-inverting amplifier, the final gain is an A, or you can say is an A log. Now these are from control concept. Now, people study control, right? You can also can divide the block diagram. You can see that this control concept is a open loop gain, and then you have a feedback network, and then difference in the input. Beta is a feedback factor. Feedback factor is a sample your output, feedback a fraction of your output to the negative input, not positive input, right? It's a negative feedback. You put in the positive terminal here. If it is a positive, if the negative will not work. The negative is a negative feedback, right? Now this is a model using the op-amp to prove it. Using control concept, you can prove it. Now, the A beta is can be small. A can be large, for example, 1 million, 100,000, 10,000 open loop gain, right? They are not infinite. Ideal op-amp A is infinite. Practical op-amp is talking about 10,000, 100,000, or 1 million, right? This is a open loop gain. Beta is a feedback factor. Now you can using the resistor to calculate the beta. Right here, the feedback factor is R1, right? Over the sum of two resistors to create the feedback factor. Because you sample the output, you feedback a fraction output to the inverting input, and this allows a potential divider function, right? Okay, so after doing that, right, you can easily to have all the design formula. Now this design formula is very important because in the design assignment, you need to find the bandwidth of the op-amp, causal bandwidth, right? You have to simulate, right? So you need to know what is the UT gain frequency, or beta. Now you can see that because A beta is much bigger than 1, so you can approximate by beta. So if you know the feedback factor, you can indirectly to calculate the causal bandwidth, right? Causal gain, right? Causal gain is about 1 over beta, about, right? Because of the approximation. So because we know that, right? Causal gain is a FC over ACL, right? And ACL is equal to about 1 over beta. You can see that the causal gain is a beta at T. So if you know the feedback factor, you know the unity gain bandwidth, then you can calculate the causal gain. Now, how can you know the unity gain bandwidth? Data sheet, right? They tell you what is the unity gain bandwidth, right? Feedback factor, your design, right? What is the resistor you choose? You can choose your design based on the given unity gain bandwidth from the data sheet. Then you can know what is the causal gain. So you need to understand the relationship between the causal gain and the causal bandwidth. Now these are proof from control, right? You can have this kind of model, feedback factor. Now this is a law inverting. Now you can see that this feedback factor is also appear here, right? Called B here. This is a beta. It's a feedback factor. A is here, but in the non-inverting, you can see that this is a B minus 1. Now you can see that you can prove it, but it's not so straightforward. I can show you some hint to prove it, right? For example, okay, this is a V in, this is a V out, this is an open loop gain. You measure this V epsilon. Remember that you are not ideal M, right? Ideal M, V epsilon is a 0. When A is a finite, you will absolutely have a something, right? Right? You apply the potential difference. V epsilon, how do you relate output and the input? Now remember that V out is a V epsilon times A, right? But negative. This is equation 1. Okay, equation 1 you can establish, right? V epsilon times the A, the overloop gain, you will get output. Now remember that you have the two sources, right? This is V epsilon here. Ideal of M, V epsilon is 0, right? Along ideal of M, the V epsilon is not 0. Now you have a source V in, you have an output V naught. So what to do? Superposition theorem, right? The next is using superposition theorem to prove it. So I suppress V naught, right? I suppress, I want to find this point V in, right? So I suppress V naught, right? We can say that you suppress this one. Now remember that this is R1, this is R2, so V epsilon, right? Will be equal to V in times R2, R1 over R2, right? Now you have this V epsilon 1. You suppress a V naught. You suppress V in, you go to V out, right? So the V out times R1 over R1 plus R2, right? This is a V epsilon 2. Epsilon 1 and epsilon 2, right? The excitation response, right? On the virtual ground point, sum together, then you can get this equation 2, right? So you're solving equation 1 and equation 2, and then you construct the block diagram, and you can find this. Okay? So the block diagrams come from establish the non-ideal equation using superposition theorem, right? And create a block diagram. Okay? And signal flow, right? And you can find that this is the block, right? For the controls people to use it, right? So you can see that if you look at the function, so you can see this one non-inverting is here, but non-inverting you add another one, right? To create the block. So that after you do it, right, you can find that this is a transfer function, right? Closed loop gain, right? B minus 1 over A. After you solve it, is a R2, R1 negative. After you solve this one, you have a 1 plus R1, R2 over R1, right? This one corresponds to here, right? And this one, you have a V out over V in, R2 the ratio, after you solve it, right? So, both can give you the block, right? Signal flow, right? For the control. This is a control concept to do it. Okay, this is a control block diagram. This is your op-amp diagram. So you can prove from op-amp theory, or you can see from control theory. Also give the same identical transfer function for closed loop gain. But you can see this is a model. Okay. Okay. Any question up to this part? All right. So I think you can try to prove it. Now upload to NTU-Learn. You don't need to copy, right? Now we go to the question. Now we studied a lot of basic, right? Why we need to know basic? Without knowing the basic, you cannot able to take to the problem, right? For non-ideal op-amp. Now we try to look at the ideal non-ideal op-amp. One example. This is an example for non-ideal op-amp. Now non-inverting amplifier. So your brain already come out non-inverting topology, right? Now the question methods definitely not necessary to give you the diagram. You need to know all, right? Inverting or inverting different amplifier, right? These are the ones you need to know. The voltage source applied to the non-inverting have a series resistor. So that means the source, right? Last time you analyze the source, no source resistor. So you can imagine that a resistor right? Right, you have a resistor, right, on the source. Right? Try to interpret the question. Okay, you have found out the expression if the op-amps are ideal. You have to understand what's mean by ideal, the key word, right? The key word is ideal. Ideal means no offset, no bias current, right? Virtual short, right? Identical, right? The potential, infinite bandwidth, right? Right? Output can go to the supply, right? No saturation limit, right? The limit is on the supply, right? Go to the full supply. This is ideal, right? Find the expression for it. Now the next is consider if it is a non-ideal. You have a bias current I plus I minus and offset, and we found the expression when Vs0. Now Vs0 means signal source 0, right? When signal source 0, you only consider offset, bias current. This is a DC offset only. The question implies it's a DC offset, right? Because you not consider the 0. This part compare A and B if the Vs is non-zero. So your signal source will come in. So your output will be superposition failure, right? All the offset components add together and all the signals and together with the signal source, right? 1, 2, 3, 4, right? Here is a 1, 2, 3, right? Here is a 1, 2, 3, 4. Last part is to give you some design example. Now you have non-inverting, the resistor R2 is 100K, Y1 is 25K, so you have 1 plus R2 over 5 times. Now you have a base current given to you. And the offset current, offset input base current is negative. So the I plus minus I minus is not 0, right? It can be 0, it can be not 0, right? So these are, you have to solve the expression, right? Do expression to solve, right? So I bias, this is a difference. I plus I minus is a negative. Equation 1, equation 2, to solve 2 unknown. You're able to solve, right? 2 equations to solve 2 unknown. 3 equations, solve 3 unknown, right? So you have to use 2 equations to solve 2 unknown. What are the unknown? I plus, I minus, and offsets are given. What value of RS to help you to do to contribute to minimize the DC offset? And we look at the design expression later to find out what is the impact for RS. Okay, now this is a question. We look at some of the solution to do it. Okay, now number 1, right? You assume it is an ideal N, everything subclass. So you have the source resistance there, right? You have to draw the picture. Better to draw, if you know, in mind it's okay. You can write direct. Better to draw the picture, right? Now for ideal M, is any current go through the RS? Now remember the source this time have a resistor, right? RS. Now ideal, no base, no current, right? Don't absorb any current. So voltage drop on the RS is 0. So because of that, right, you can see that this point potential Vs in here will be equal to Vs in here. So in other words, your input signal, right, measured from this point to this point is equal to Vs. So no current go for RS, so the voltage drop is 0. So the V equal to Vs, so Vs multiplied with R1 to R1 over R2 over R1, right? Very easy, right? Ideal M is very easy, right? Now this time we go to non-ideal M, so you have to draw the model. You have when you're talking about the second question, your Vs is compared to 0. Now when Vs compared to 0, what about the resistor? Still there, right? Still have resistance there, right? Rs. So you cannot say the resistor not existent, right? Because the question say you have Rs associated with the source resistor. Okay? Now here you have to analyze the op-amp, right? With DC offset output contributed by I plus minus and Vi naught. So the Vs will be 0. You amplify it. Now how do you analyze it? How many sources? 3 sources, right? So you have to draw 3 pictures, right? To analyze 1 by 1, right? And sum them together using superposition theorem. Now, superposition theorem only apply for linear system. How do you make the system linear? The system is main linear when you apply negative feedback, right? So you apply negative feedback, the system becomes linearized. When linearized, we can treat it as a linear system. When under linear system, we can apply superposition theorem. Superposition theorem cannot be valid if the system is nonlinear. This is a circuit theorem, right? Circuit analysis. Okay, we do one by one. Number one, right? We analyze this picture, only the offset sources, right? Offset sources, we subtract all the bias current. So very straightforward, right? No bias current because suppressed, all the bias current suppressed, only offset sources. No voltage drop on RS, you directly amplify for networking. Next, consider I minus. So we draw the picture. Better to draw the picture, right? It's a I positive, right? We consider picture I positive. We subtract I naught, we I naught, we subtract I minus. And because going into the op amp, currents are going upward, right? When you measure the potential reference to the ground, negative, negated. So the current and resistor forming voltage source, a negative voltage source, amplified by non-inverting gain factor. Right? Very straightforward. Like last example, you see the tutorial 1, question number 6, right? The last part, offset comes from I minus. Now remember that we ion cancel, right? You only consider the I minus, I plus also suppressed. No current go from here. The resistor short to ground, that means this potential is a 0, right? This potential is 0. Because the 0, this point also 0. Because the gain is a high gain. 0 here, 0 here, no voltage drop. So this is like a ground. And your current is supplied to here to here. Because this is like a ground potential. So you measure from this point to ground, equal to this, measure this point to here, because this one is a ground, right? So the product, right? Now what is the interpretation? If you compare the two bias current, this is a negator. This is a positive, right? Under superposition theorem, right, you sum everybody. But you can find that one of the offset counteract with another offset due to the different polarity, right? So what happens if you deal with different polarity? You reduce it, right? If you properly select the magnitude, right? So after doing that, you sum everybody together, right? So this is your answer. The total DC offset contribution by 3 components. But you can see that this one, if this is a positive, this is a negative, you can see that there's some cancellation, right? How do you cancel the offset? If you based on the question, but the design and analysis is a very good thing. Why? Because it tells you the insight, right? On the individual component, right? Contribution. But you find that the component have different polarity, right? Right? This polarity is different than the other, right? So if I select the source resistor appropriate value, right? We can cancel the other offset, right? Because the sign is negated compared to other, right? They are counteract each other. So by properly selecting the RS, you'll be properly to cancel the offset. So if you include the signal, right? Everything add together, but you add the signal. Under the signal, it is still non-inverting, right? If the signal is not non-inverting, that's why you add a non-inverting function. The transfer function for these two components, same. This one, the I minus, not the same, right? The transfer function is different, right? Now the last part is to cancel the offset. We do calculation first. The calculation is substitute all the parameter. Now I say that there are two equations. You solve the I plus and I minus. They are not the same, right? They are not the same. Sometimes the question say I not equal to 0. That means you don't need to solve, right? If there are bias current there, that means they are identical. But you have a bias current but not identical. That's why you have solved the two linear equations to get two unknown come out. Now why you need that? Because you have to apply to analyze it. So the offset is given 2 millivolt. You can see that this is the total output, right? You see before. So you can observe that how can you allow the DC offset? When you allow the DC offset, you are not considered the signal, right? You are considered offset mounting. So you solve the equation, no? I set this to be 0, then I can calculate the RS component such that you can know the offset. Right? After you equate this to 0, you one equation, one unknown. After you do it, 55K. So in other words, right? If your source resistor is a 55K, right? 55K, you can mount all the offset, right? So it's a offset cancellation, okay? Any question up to this part? Any question up to this part? Now, the goal is to draw the picture, find out the topology, inverting or non-inverting, and then apply superposition theorem, sum every term together, right, and interpret the result, or calculate the value if the data given to you, right? You can calculate the value at the end, right? So the step is a very routine, right? You follow the step. Even though circuit is a very complicated, it becomes easy, right? The problem becomes like an exercise, right? In the beginning, you don't know it's a problem, right? Once you know it, it becomes an exercise only, right? So you make use of this type of knowledge, right? To analyze your circuit to the lab, right? To the lab. Apply to the lab, right? Offset is one of the items inside your design assignment. Closed loop measurement also the design assignment. So you need to understand the principle here. Any question? Now we look at another one. This one is a bit challenging. High gain circuit. Now high gain circuit, right? You have an inverting amplifier in cascade. Remember in series means in cascade, right? One amplifier and then the other one, right? Now inverting. Now this is a keyword, right? You need to know what's a keyword. In the exam, nobody tell you draw diagram. You have to draw yourself, right? Sometimes, right? Sometimes they give you diagram. Sometimes they don't give you. And you have to look at the keyword, right? Two inverting cascade together. Supply is a 15 volt. Now remember that you have a supply constraint, right? Your M can, no matter how much your output, right? You cannot more than the supply. Constrained by the supply. The first day have a gain of -20. So that means the first day gain already known, right? The ratio of two resistors divide -20. The second state not known, they don't give you, right? So your R2, R1 in the second state not sure. The first one already divided for you, but you have to see the work, right? The output no closer to supply. Okay, 1 volt. Meaning that ideal supply is a ±15 volt, right? Your ideal output should be go to ±15, right? Plus 15 volt and -15 volt. But in this case, it's under saturation constraint, saturation limit, right? For non-ideal M, you can go maximum is only 14 volt. Another is a -14 volt. You cannot more than that. Okay, that is a problem. So this is one. What is you have to find, right? You have to see that offset is given to you. Bias current is 0. IO is 0. What does it mean? If this question gives you, what is the interpretation? Bias current is not in the picture, right? Right? Because there's 0, right? I not 0, I by 0, right? So not in the picture. What are they in the picture? Vi not, right? So you have to consider offset model, Vi not, and no bias current. 2 of M in cascade, analyzing the second stage gain, right? Now if the both stage work in linear region, find the expression for the output in terms of Vi not. They never ask you the I bias, but because it's already see this as 0, right? First stage gain and second stage gain is quantified by these two alpha 1 and alpha 5 negative. Okay, let's look at somehow to attempt it. Now, the second question is that if you have signal is 25 millivolt peak sine wave, what is the maximum gain in the second stage? With VL is under the saturation limit. Okay, so you apply the signal. Now remember that we discussed the tutorial 1, right? Have an offset, right? The offset will affect your actual swing condition. So we will look at the picture and how to, and from there to analyze the circuit. So we will go to the answer here. We are not, right? Right? Will be identical in this example. They may not be the same, but in this example, they give you identical offset, a 0 bias current, so we not to worry about it. The first stage gain is negative 20, right? Second stage is unknown, so we need to solve the unknown in the presence of the offset. Normally we calculate, we don't have an offset, right? But in the present offset and in the presence of saturation limit, the two are non-ideal effect. One is we are not offset, the other is saturation limit, right? Plus minus 1 volt below the supply. So the maximum you can go is 14 volt or minus 14 volt. How much the gain you can set on out4 and out3 in order to avoid the saturation limit issue, right? Okay, so we have to look into the analysis. Now you can see that we can using superposition theorem, right? One source, two source generate this point, and then another source and this source generate another one. So superposition theorem. I think it's a very straightforward. I'm not to detail, but I think you should be able to. If you look at the expression here, the output one will be about 2 components, right? You subtract the Vi naught. The component Vn will generate inverting gain. The Vi naught will generate non-inverting gain, right? Non-inverting gain, right? One inverting, one non-inverting. Okay, now we contribute the total output on VL1. This is an intermediate point. That is 2 components combined. You have signal and offset. Now you can see that it's not just a signal going in, right? You have an offset going into the input for the second stage gain. Input for second stage gain, right? These 2 components, right? Treat is like a source, right? You combine everything like a source, right? This source will be amplified by the inverting gain, but the offset in here by the non-inverting gain for the second stage. Because the Vi naught for the 2 stages are identical, we write identical. They may not be the same, it may be VIO1, VIO2, right? Okay, after that, what is a solution you can solve? You have output 2 and the input is a key point, right? Together with the offset. So in the midday point is a VL1. We have to substitute the VL1, right? Into this is equation 1, this is equation 2, the VL1 into here, and then expand all the term. This is the answer. Now I'm not going to for you, you try to convince by yourself, right? You substitute VL1 into equation 2, from equation 1 to equation 2. After you solve it, you will find this expression. Okay, we have a little bit an intuition to realize the term. Now, what is the intuition telling you? Right? You can see that if you don't consider the offset, right? You consider the signal. Signal is amplified by 1 time for first stage, second time for the second stage, Now, this is inverting and inverting, right? Invert and invert. What about the output related to signal? Non-inverting, right? Non-inverting. So you can see that from the signal point of view, right? The Vs will be non-inverting. Now these are non-inverting amplifier, right? Construct by two inverting amplifier in cascade. Invert and invert, right? You go to inverter, another inverter become non-inverting, right? So this is intuition, right? Now you can see that for this offset, right? You have a generally, if you look at the first offset, the output is inverting, right? Inverting offset. So the inverting offset, right, will generate R2, R1 offset. Now, R2, R1 offset, if you don't consider this offset, the offset go to here, right? You can see that the offset go to here is also inverting offset, right? Invert and invert. So you can see that this is an invert, and this is also this one non-invert. Sorry, this one if you ground this one, this is a non-invert. 1 plus something, right? 1 plus R2 over R1, right? 1 plus something, non-invert. So non-invert, you go to another state. This is an invert, right? Right? So you are offset, right? If you look at the first offset, you have 1 plus R2 over R1, and then you multiply R4 over R3. Okay? This is a first offset outcome, right? From the first state, you cascade gain, right? That's why high gain amplifier is more challenging for low offset design. Now you expand the term, right? Now remember that you're gonna come out, right? Now this one, right? This one you multiply together, right? Now you look at that, you have a product. So you get a negative offset, right? How about this one? This one is also a negative offset, right? So you can split into two terms, right? Right? Split into two terms. Okay? So one term is a cascade gain, one is a second stage gain, right? So the first offset, right? You go for one stage, another stage, right? You come out, you can split into two terms, right? One is a cascade gain, right? So this is the one you see, right? How about the second one? The second one here, okay? Now, but because the second offset, right? What about the second offset? The second offset from the second stage is a V offset plus 1 plus R4 over R3, right? So you can see that when they add together, right? This one and this one cancel, right? At the end you get plus offset. So you can see part of the offset component, right? From here will be cancelled with part of the offset component from here. At the end you left V offset. Okay, so this is a formula, right? Intuitively you can able to interpret, right, the design. Now you look at that, right? There's some partial cancellation for other term, so you can definitely write out here. So the VI naught here is insignificant because you don't have much gain. It's a high gain, right? You can see that VI naught is a positive 2 millivolt, negative. Vs can be positive, can be negative, right? Why Vs can be positive, can be negative? Anybody can tell me? Because of AC, right? You may have peak signal, right? For Vs, negative peak signal for Vs, right? You can be, because sinusoidal change, right? So, you'll be very careful about, now if you look about the 2 millivolt offset, right? What you think about the output? right? You look at the picture, right? And for bipolar supply, your offset should be here, right? You don't have offset, right? 0, right? You can swing. Right? But unfortunately, right, you have VI not positive 2 millivolt, but negative, right? So what about the offset component? Your offset component will be here, right? Right? If you look at the point of view, what happened to your negative swing is a more stress than your positive, right? If you look at the symmetrical swing, right? Right? You can see that the offset is shifted negative, right? So what is a value that will affect more seriously is a negative value, right? On the VS. So that is the answer for here. Now, ideally symmetrical here, low offset, but your offset is shifted low based on the equation, right? To indicate. So you want to be symmetrical, right? The negative constraint, right? You affect the negative swing, right? You affect the negative swing. So that is why you're using the VS as a negative, right? Now VS is a sine wave. You can go up, go down. Go up is a positive, go down is a negative, right? But when VS is a negative, you are the worst case, right? You are the worst case. We consider the worst case, right? Because VS negative will be the worst case condition. So we are using negative 25 millivolt as a worst case. Okay? So after you do it, you can calculate right? You can substitute here, right? There is a formula here. Negative 25 millivolt is a worst case. You know this. You know this is unknown. This one you get it small, and this one 2 millivolt. You solve, right? Minus 14, right? Because this picture is affect the negative side, not on the positive side. Negative positive side, saturation constraint is 1 volt below the negative supply. So because of that, right, you will have 12 volt. You solve this expression, you will find that this minus 26. Okay, minus 26 is a limit. If you check the minus 25 positive for the design equation, you have a subtraction. That means you will not be go to saturate, right? Only 12 volt. So the answer is you have to look for worst case, right? From the offset point of view. Because the situation is the offset caused the level shift downward, right? So in order to make it worse, it's a negative VS, not positive VS. You'll be very careful about this. Okay, after that you will solve this one, right? Any question up to this part? No question, right? Okay, I will upload to NTULearn and you don't need to come here. Now we look at another one, chill rate, right? This one will be used in the design formula when you go to the design later on, right? Now we go to here. There is a talking about question number 3. Number 3, this is the last question we talked. Op-amp is inverting configuration. So you should know that is a negative side, right? Ratio of 2 resistors will give you 50 times. Now you can see that the op-amp is a non-ideal, have a slew rate. Now the ideal, so although it's a non-ideal with the slew rate, but the offset component is not considered here. So you have to see the question, right? And apply your analysis according to the stated requirement. So you're not worried about the offset here. Now if the input signal is a 10 millivolt peak sine wave, what's the maximum frequency you can come out right? Or the slew rate limitation is reached. Okay, now this is a sine wave. You found out the worst case maximum frequency, right? When slew rate start to appear. Now remember the slew rate is talking about worst case rate of change of output with time. Output, right? Not input, right? Here is a given you the input, right? You need to find out the output, right? Now you'll repeat the A if it is a triangular wave, and then you repeat when it is a square wave, or look for the slew rate. Now we look at the first case. Now we can see the closed loop gain is 50 times, and you have a repeat sine omega t. Now remember the slew rate, what is the mean by slew rate? Rate of change of output with time, worst case, right? Input, how do you relate input with output? You need to closed loop gain, right? Multiply the closed loop gain, right? The closed loop gain is a 15, then you will get it. Now, although your output may have some DC offset, right? Just example. But the slew rate is related to rate of change, AC, right? Nothing related to the DC. So when you differentiation, right? What's the DC type constant is 0. Don't care, right? Don't care. So when you differentiation, you have omega cosine omega t. Now, slew rate, delta V out, delta t is a SR, right? Worst case, right? Now, worst case, this one is a 1, right? And this omega is a maximum, right? So your limit is equal to slew rate. So you can easily to know that after you substitute, right? This is a radian per second. Now remember, omega is a radian per second. When you want to count the frequency, 2 pi f, right? Omega over 2 pi. The student easily to make mistake relation to omega and 2 pi, right? You will be very careful. This omega unit is a radian per second. When you find the frequency, V1X. So if you have V1X6, V1XK, V1X kilohertz, right? You will know distortion. Now remember that your amplifier, the input is here, and the output, right? Just nice, right? Amplify the signal. This is a V1K maximum. Below that, no problem, you can follow. If you're above V1K, what happened to the waveform? You already exceed the slew rate limit, right? From sine wave, although sine wave respond, but you already exceed the slew rate limit. Let's say 1 meg, right? Let's say you input frequency equal to 1 meg, you already exceed it. Right? So what happened to the waveform? Can you tell me? It will be like that. Okay? So you can see that more like a triangle, right? From side to triangle. When they are slew rate, right? They exceed the slew rate limit. So this waveform is a distorted. Right? The output waveform distorted because it exceeds the slew rate. Right? There's a distortion there. You change the wave shape, right? Your side become a triangle, right? So this is one effect. The next effect is calculate the triangle waveform. This is a triangle waveform. The 10 millivolt peak. Here is a 10 millivolt peak on the sine wave. Here is a 10 millivolt peak on the triangle. Okay? We can see that the triangle input, right? 10 millivolt peak. And you know that the slope is here. The slope is 20 millivolt peak over T over 2, right? This is a divide VP, and this slope is this vertical is 2 VP. The slew rate is a maximum rate of change of output over the duration T. But this is a T over 2, right? So 10 millivolt becomes 20 millivolt. T over 2, right? The T over here becomes 4, so you can 40 millivolt over. So this is an input slope, right? This is an input slope. Triangle rate is an input slope. You see what we want? Slew rate is a rate of change of output with time, right? we need to know output slope, right? Not the input slope. So multiply the gain, you multiply the gain factor, and equate the slew rate, you'll find that 500K. Okay, if you do a triangular waveform, right? Now this is your waveform. And this is your triangular waveform. Okay? You are faithfully reproduced but inverted. Now I ask you another question. If you're more than this frequency, 500K, right? Let's say 1 meg. How does it look like for the triangular waveform? Anybody can answer me. Slew rate distortion on the triangular waveform. Now, slew rate distortion on sine wave is to become a triangle, right? What is the slew rate distortion on triangular wave? Huh? No. It will be smaller triangle. Okay? So it's still triangle, but smaller. When you further increase the frequency, it will be also triangle. Right? Okay? Distortion in triangle is also the same, but the magnitude reduced. Okay? Slew rate distortion to the sine wave, you see the slew rate from sine to triangle. A triangle is still triangle, and they distort, but the magnitude reduced. Okay, interesting, right? Okay, the last part is a square wave. So the square wave, right? The square wave to the input, right? It's like a pulse, right? Right? 90 degree, go high. Now remember that if you look at the response for slew wave, you should infinite slew wave to respond to pulse, right? But are you able to hit the infinite response? No way, right? You're limited slew rate effect, right? So at the end, it's a trapezoidal. Okay? So your output response, right, is from square become a trapezoidal, right? So this is a response. And the output, right? So the square perfectly go up, perfectly go down, but due to the, definitely will exceed your slew rate. Because the slew rate have a number, right? You go up straight, go up down is an infinite slew rate to meet, right? Only ideal OM can do. But all the OM is not ideal, right? They have a finite slew rate. So all the OM to respond to the square wave become a trapezoidal wave output. So that's why you can see trapezoidal wave output. Now remember that 10 millivolt peak, right? So multiplied by 50 times, right? You can see 0.5 volt. Here is a 1 volt, and the time is based on the slew rate is 1 volt per microsecond, right? This is a 1 volt per microsecond. For 1 volt swing, the time meter is a 1 microsecond, so you can draw the waveform. You must have a distortion in this, there's no choice. Square wave cannot avoid, right? So because M is a limit on the slew rate, so there will be trapezoidal, right? From square to trapezoidal, from sine to triangle, from triangle also triangle but smaller than magnitude. This is a slew rate distortion. Okay, that's overall for today. Any questions? Now next week, well, we will know more tutorial to go through. We will be continue on the design assignment, start the design assignment, right? You have to do the assignment. Now you try to load the LT spine, learn the spine, how to draw diagram, flex the component, use the computer, the component, do some basic simulation, right? Now I will do the demo next week. After the demo, we will go to